Okay, now for our next class activity, we're going to read sections 3 through 4 of chapter 9. So you need to have read those thoroughly to apply those concepts here. And we're going to look at concept questions 7 through 12, and then exercises 14, 19, and 49. So starting with 7, concept question 7. Go ahead and go look at that and see what you can make of it. All right. So number 7 has this weird problem. We have a particle that starts here at this location A and does something like that. It's not exactly like that. The exact shape's not important, but this is a vertical circle, so up is that direction. And the question is, what is the work done by gravity on the particle as it goes around this circle? Okay, so what is the main idea here? What is work done by gravity mean? Okay, so work generally means a force times the distance, and more importantly, the force in the direction of the displacement. Okay, so when I say force times the distance or force over distance, it's this force multiplied by the displacement of the particle. Okay, so the particle went from here all the way over to here, but the force is always pointing up. So one way I could do this is I could say that I could do the force times the displacement times the cosine of the angle between them. Okay? And if I were to think about that, the force is constant, but always pointing straight down. My force is constant, pointing straight down. Okay? So this cosine of theta means I want the amount of force in the direction of delta S. I could actually rewrite that and say I want the displacement in the direction of the force. I could tack this cosine of theta onto delta S and get the same thing. And so what I really want is F delta Y, because F is in the direction of Y, or negative Y. And when I think about that, as I go up some amount, I have I can model this piece right here as going up and then over, up and then over, up and then over and then up, over and up, over and down, over and down, over, down, down, over, and continue to do that all the way around this loop. Now, if I add up all the vertical displacements all the way around this, well, guess what? I end up back at 0. Because for every time I step up, I have to step down. And so for each little step I take, they all add up to a delta Y of 0. Now, we could have jumped to that actually a little bit faster and just said that for a closed path, meaning I end up where I started, I'm going to get work done is 0. And that can come from work being equal to an integral of S initial to S final of our full-blown form, like that. Well, no matter what the integral is, since it's adding up the area under the curve, if I end up where I started, I have to backtrack. And that means that for this constant force, I should add that this force is constant over the whole path. Then that comes out, and I just have 0 minus, or I have final minus initial, and the final is the same as the initial, and I get 0. So in this case, for constant force, that would be 0. So we can use this now as an example to say that work over a closed path, I'll call it a loop, but it doesn't have to be circular. It could be any path where you end up where you started. That is always equal to 0. I guess it should say for a constant force. Always equal to 0 for a constant force. Okay, so with that, we've learned something there, applied it to this problem. Now, let's learn some more stuff. Go on to problem 8. Sorry, this is concept question 8. Okay, So what's more, lifting a block straight up? How much work do you do lifting it straight up? I can call it F1. This goes through a height change of h. Well, the work done in that case is what? Okay, it's force times the distance of displacement, and it went up a height h. They're in the same direction. The displacement is up. So I get F1h. Okay, well, what in the second case? I've got a ramp now. It's a height h. Makes an angle theta. And this block moves now a larger delta s. And in order to achieve that, I'm going to have to apply a smaller force. Okay, and so now I'm going to get that the work done is F2 delta S. Okay, so that's F2 delta S. All right, well, how are F1 and F2 compared? How's delta S compared to H? Well, I can see delta S compared to H actually fairly quickly. Delta S, or I should say sine of theta, is equal to opposite over hypotenuse h over delta s. So delta s is equal to h over sine of theta. So I can change this. F2 equals, or work is equal to h, F2 times h over sine of theta. Okay. Now, how does F2 compare to F1? Well, if this is moving at constant speed, the problem suggests to assume it's moving at constant speed. That means acceleration is 0, and so my upward force must equal my force of gravity. Okay, so this is actually mgh. That's the work done by this force, by the force you'd have to do that. Okay, well in this case we have a little bit more complicated scenario. I've got tilted coordinate system, and my force is this way. Okay, now my gravitational force is this way, and it has a component opposite that, and if they're moving at constant force, or constant acceleration, these two must be equal. So this is Fg, and this is theta, always measured from the normal component. This would be Fg sine of theta, okay, and this is F2, and so that means that F2 must be equal to Fg sine of theta because they're at constant velocity, no acceleration. So if I plug that in now, I get mg sine of theta times h over sine of theta. Thetas cancel out, and I get mgh. And so according to our definition of work, that if I'm pulling at constant speed, okay, so constant speed in either case, now it could be one's faster than the other, but as long as it's constant speed, the amount of actual work I do is the same no matter whether I pull it up a ramp or pull it straight up. And we're going to be able to, in the next chapter, actually embellish that idea and talk about potential energy. This is actually equal to the change in potential energy of the system for the gravitational potential energy. So hold on to your seats for that one in chapter 10. But the important thing is we applied our idea that we had force in the direction of motion, and then we just had to relate them by their kinematics, dynamics, and geometry. Okay, let's move on to exercise 9. Okay, for 9, right, we have a ball that's traveling around the circumference of a circle, ball on a string, so you're swinging this ball around on a string. There's a ball pulled on a string, and it's moving around this circle. Okay, what is the work done by the tension in that string? So think about our definition. So the displacement is tangential. Our delta S is tangential to the circle. And it's not zero. It makes it, delta S is equal to 2 pi r. Okay. But what's important is that it's tangential. The motion is actually tangential. Now the tension is non-zero, otherwise the ball would fly off. So we have a non-zero tension, but it's pulling inward constantly. So when I think of the work done, I think of the force in the direction of motion times the displacement. But what we have is we have the force in the direction of motion. There is no force in the direction of motion. This is perpendicular. F is perpendicular to delta S. And so F sub S is equal to 0. There is none. Okay. Now we could have seen this also with this being equal to F dot delta S and written that out as F delta S cosine of the angle between them. And the angle is 90 degrees at all times. And so cosine of 90 equals 0. We would have gotten 0 again. Okay. So again, emphasizing that it's not just a force times a distance. It's the force in the direction of motion. And so perpendicular forces can do no work. There is no work done for any forces that are only causing a direction change, like all of our centripetal forces or forces that cause a centripetal acceleration. Okay, so we've emphasized the need for direction with dealing with work. Okay, now take a look at 10. Okay, this is an interesting one, and it adds another important point of thinking about work. So we're adding a whole bunch of details about work. Okay, so a sprinting block is a thing on a track where a person's, forgive my poor, okay, that's a person's foot. They're pushing on this sprinting block, and they're in a crouched position, and then they extend their leg, and they push off. And the question is, what's the work done? What's the work done on the sprinter as they're pushing off? Okay, now think. There's a force there. The sprinter pushes back, which by third law, the block pushes forward. But what is the displacement? Does that block go anywhere? Does the person's foot go anywhere? Okay. It doesn't. Delta S at that contact point is 0. Now you might be saying, well, the person's center of mass goes forward. That's very true. And so we need to be more careful than just saying a displacement of the object. We need to actually say a displacement of the point of contact of the force. And so in this case, the force is being applied to the sole of the foot, but the sole of the foot doesn't go anywhere in this time. So there is a force acting on the person, but it does no work. Okay. So here's another case where the work is 0 because delta S of the point of application of the force is 0. Okay, so that adds to our criteria to understand work. Okay, now let's consider problem 11. All right, so here's a different thing. We're going to talk about spring forces, which you have some experience with. So this is going to be a bit of review. All right, so we know that Hooke's law says F equals K delta S. What's important is that delta S is the stretch or compression from equilibrium. K is the spring constant, and F is the force of the spring. Now, there's technically a negative sign here if I wanted to put vectors. The negative sign just means it's a restoring force. If I pull on the spring, the spring pulls back. If I push on the spring pushes back. So that's what the minus sign means. So we're just going to look at magnitudes here. So with this, question is, well, if I stretch the spring 1 centimeter and I get this force F, then how much should I stretch the spring to get a force of 3F? So the answer is 3F. So 3F, since K is a property of the spring, must be 3 delta S. If I call these 0, okay, if F equals 3F0, then delta S must be 3 delta S0. Okay, so if it was 1 centimeter, then this one must be 3 centimeters. And the next problem, well, what if I compress it and get a force of 2F0? Well, then that's going to have to be 2 delta S0. So the spring must compress 2 centimeters. So compression and stretch don't really mean anything in terms of the size of the force. It's just that the force is a restoring force. It always opposes what you do to it. Okay, 12. Let's do 12 here. This is a good one too. And so you attach a spring to a wall and then pull on it with some force. And it stretches a certain amount, delta S. And then you take that same spring and 2 people pull on it, each with the force F. And the question is how much has this string stretched in this case? So go think about that one. Okay, so you might want to say, oh, it must have stretched double because I have twice the force pulling on it. The answer is that the stretch is the same. If there's 20 centimeters here, it's 20 centimeters here. I'm saying, well, but you're pulling on both ends. You're pulling with twice the force. Well, let's look back up on here and look at the contact point of that spring to this wall. Is the wall pulling on the spring when you're pulling on it with the force F? If you think about it, you are. If that wall was made out of paper, then that spring would pull right out of the wall. So the wall has to pull back on that spring. And in fact, if the spring's not going to accelerate, then that wall better pull back with the same size force of this. So the wall is pulling back with the same force F as this friend here is pulling. So these two scenarios are exactly the same. The force must be equal everywhere within the spring in order for Newton's second law to hold. Okay, so these are the same scenarios, so delta S is the same. All right, let's now move on to some of the exercises. So look at exercise 14. Okay, this is practice with our dot products. So this is emphasizing, we're just trying to emphasize our use of the dot product, this vector dot product, to do work. But we want to practice with the math alone on this problem. And so we have this vector, A, and we have this vector, B. They're separated by an angle of 40 degrees. A is 3 units long and B is 5 units long. And we want to see what A dot B is. Okay. So what is A dot B? By definition, it's the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. So this is going to be 3 times 5 times cosine of 40, because that's the angle between them. And if you plug in your numbers, you're going to get 11.5. Now we can assess that. Does A have a component in the direction of B? It does. I could draw a perpendicular. I can see that there's a component of A in the direction of B, about that much. And so that component, being in the same direction, should give me a positive value here. So this is greater than 0. That's what it should be. Okay, now let's look at a different case. We have a vector C and a vector D. C is length 2 units, D is 3 units, and they make an angle of 140 degrees with respect to each other. Okay, so if we do C dot D, what does that equal? Okay, it should be 2 times 3 times cosine of 140, and the number you get is, it's negative 4.6. That's less than 0. Should it be? It should be less than 0, because if I look at C and break it into components, I get a component that way and a component that way. This component right here is the component of C in the direction of D, along the line of D, but it's opposite it. And so I should get a negative. Had this been a force and a displacement, this would have done negative work. So this is correct. I should have got a minus sign. Okay, finally, we have this. These two vectors. Okay. This one's of length 3, this one's of length 4, and they make a 90-degree angle. So what is E dot F? Okay, it is 3 times 4 times cosine of 90, and that equals 0, because cosine of 90 equals 0. And it should be 0 because there is no component of E in the direction of F, or likewise no component of F in the direction of E. These are perpendicular, which means the dot product between them is 0. Okay, so all of these are just generic math practice, but we can see how we could apply it to forces. This could have been a force and a displacement, or a force and a displacement. Same with these two examples. And we would have expected certain values of work done, a positive, a negative, or 0 work done. Okay, now we're moving on to number 19. Go ahead and think about that one. Okay, here's another practice with work. Basically, we're going to apply this math to our definition of work. So we just have to be careful. Here's our box. We have one force, T3, pulling backwards. We have one force, T1, pulling at an angle of 20 degrees up. We have another force, T2, pulling at an angle of 30 degrees. And we're told that the displacement is this direction. Okay, the displacement is 3 meters. Okay, and we're given values of these 3 tensions. So what are the work done by T1, T2, and T3? Okay, let me just quickly ask, should the work done by T3 be positive, negative, or 0? Okay, so it should be negative because the displacement is this direction, T3 is backwards on it, and so that should be negative. These two should be positive because they both have a component in the direction of the motion. Okay, and so they should be positive. So we've got for the work done by 1, going to be T1 times delta S times the cosine of the angle between them, which is 20. And that's going to be equal to 1690. In like manner, we can find the work done by 2, and you're going to get 1065, plugging in 30 degrees for its angle. And if we do T3, we plug in its value there, but we're going to get cosine of 180 degrees, which gives us the minus sign, 1980 joules. Okay, now let's move on to the last problem, problem 49. I'm going to try and conserve some paper here. So problem 49. Go try and work on that problem. Okay, so we have an ice skater who's moving due north and has a displacement due north. Okay, this is north. And they're skating on the ice, and the ice has no kinetic friction, but the ice skates make a groove in the ice such that there's a slight static friction perpendicular to the skates. Okay, so there is a force this way, a static frictional force, that's opposing the component of a northeast wind that applies a force northeast. And so it applies, so this frictional force, okay, I'm going to call this perpendicular to motion, and then there's a component that is parallel to the motion. Okay? And so this frictional force keeps the skater from sliding sideways. Okay, can we use the work kinetic energy theorem to find out how fast the skater is going after they've gone 100 meters with this wind? Okay, first of all, the work kinetic energy theorem is that work equals delta K. Now we know how fast the person is going to start. Okay, we're given that information. And the question is, can we find the work done? Because we could have K final minus K initial, that's delta K, is equal to the work, or K final equals K initial plus the work done. And so our question is, well, what's the work? So what is the work done by the wind on this ice skater? Well, it's going to be the component of the force in the direction of the motion, which I've labeled as FW parallel. It's the piece parallel to delta S, times delta S. Okay. And just so you know, when northwest means 45 degrees east of north. And so this is going to be the force of the wind, which is a 4 Newton force, okay, times cosine of 45, is the piece that's parallel, and then times 100 meters. They go 100 meters in this wind. Now notice the cosine of theta ended up on this side, whereas in some of our previous cases it was at the end. Well, it doesn't matter mathematically, and conceptually, all it was doing is pulling out the piece of the force in the direction of the motion. And so we can think of it qualitative that way as well. Okay? And so when you plug that in, you get 282.8 joules. And now we can plug it into here, rewriting this for velocity, because we're asked for velocity. We get 1/2 mv final squared equals 1/2 mv initial squared plus this work done, which we now have a number for. Okay, now solving for v final, we're going to multiply everything by 2, divide everything by m, and then take the square root. So that'll leave our v initial squared by itself. So 2 work over m, all square rooted. And if you plug in your numbers, you should get 5.2 meters per second, which is a little bit faster than the 4 meters per second the ice skater was already going, which seems reasonable. I mean, the wind's not going to make them start booking it, and they've gone 100 meters, which is a football field length, so that makes sense. They could have increased their speed by a little bit more than a meter per second. Okay, now think about part B. Part B is actually purely a review question. It has nothing to do with work. It's just reviewing forces in Newton's second law. Okay, so in part B, I hope you looked at these pieces right here, as well as the normal force. So if I'm staring at it from a back view, okay, with the vertical, I'll call that Y, and the horizontal, I'll call it X. Look, I have a normal force, and I have a downward force of gravity, and then I have this frictional force, and I have this component of the wind force that is perpendicular to the motion. Okay, so that's this piece right here. So this is a top-down view. This is the back view. I'm staring at the back of the skater. So the fact that the skater is not accelerating up or down does tell me that the normal force equals mg, and that the skater, we're asked what is the minimum value of mu s, which means that we're looking for the Fs max. Because if mu s got any smaller, then it would slip. And so that's what we're trying to find is Fs max. So using the x component, we could choose, it doesn't matter which one, so we'll do Fs max minus F wind perpendicular equals ma, but I'll just say that's 0, it's not moving anywhere. This is mu s times n, which all just for brevity, we just showed or explained that n equals mg, must equal F wind sine of theta. And therefore mu s equals F wind sine of theta divided by mg. If you do that, you get a really small number, which makes sense. This wind shouldn't be terribly strong, pushing a skater sideways. So it requires just a very little coefficient of friction to keep the skater from slipping sideways. So again, that was purely a review question, a good one, but a review question. Okay, and that concludes our class activities for today.